Many recent image editing approaches take high-level image constraints as input, for example, a change of aspect ratio, or in-painting a marked region. Some of these algorithms are interactive, like seam carving, but offer limited control over the results. For example, here we can protect some regions from changing. Other algorithms offer more control, but are too slow and memory-intensive for interactive use. In this work, we present a novel approach to image editing using high-level constraints, like drag-and-drop recomposition of an image as shown here. As you can see, our system is interactive, high-quality, and easily directable. In addition to image recomposition, we also provide tools for image completion and image retargeting. Each operation can be controlled with user-specified constraints. This system relies upon a fast, randomized algorithm for approximating the nearest neighbor patch correspondences between two images. Consider the case of in-painting a missing region of an image. Many algorithms address this problem by searching for similar patches elsewhere in the image and filling the missing region with their contents. We make two key observations about these searches for similar patches. First, random guesses for the correspondence are likely to be wrong most of the time. But in a sufficiently large region, a few lucky guesses will be almost the correct correspondence. Second, once we do find a good guess for any one patch, it is likely that many nearby patches have similar correspondences. Armed with these two observations, we begin with a random initial guess for the patch correspondences and iteratively improve the results. Our algorithm alternates between propagating good correspondences to neighboring patches and sampling the nearby image space to find even better correspondences. Although the initialization is completely random, a few lucky guesses propagate quickly to neighboring pixels in the propagation phase. The random sampling phase complements this greedy approach by helping to avoid local minima. The algorithm generally converges in just a few passes. This algorithm is over an order of magnitude faster than the state-of-the-art, enabling a new approach to interactive image editing. For in-painting, we implemented the space-time video completion algorithm of Wexler et al. Although the original implementation required several minutes to compute a solution, our implementation can be used to interactively in-paint fairly large holes in an image. The user can further control the in-painting process by constraining different regions of the hole to be filled with contents from specific image regions. In this example, the roof line was completed using patches from another part of the roof. For image retargeting, we implemented the bidirectional similarity algorithm of Simikov et al. Unlike other retargeting methods, this algorithm can simplify repetitive structures, such as the windows on these facades. However, some of the image has become distorted in the process. Here again, we provide a constraint tool to correct the results. The user simply draws lines on the input image, indicating that the corresponding lines in the output must remain straight. Here is an example of the artifacts produced by seam carving. Seam carving allows certain regions to be protected by reweighting them, as shown here, but even after reweighting, straight lines can still become broken. In our algorithm, we provide similar tools to explicitly prevent specific image regions from changing, while allowing both horizontal and vertical translation. In this example, retargeting without constraints introduces distortions in the buoy and the straight lines of the shelves, but after marking a few lines and regions, the distortions have been ameliorated. Finally, we also provide a tool for interactive image reshuffling. In this example, features on a building can be moved around very easily. In previous works, reshuffling took minutes to compute, but using our algorithm, it can be computed interactively. In this example, the girl on the left is moved closer to her brother on the right. Notice that our reshuffling tool also supports the same straight line constraints demonstrated earlier for retargeting. In this case, we want to straighten the edge of the grass in the background. In conclusion, we have demonstrated a fast algorithm for finding patch-to-patch correspondences between two arbitrary image regions. This algorithm can be employed in a wide array of new and existing patch-based image manipulations, enabling novel workflows for structural image editing. In addition, we believe it will be useful for many other applications in media synthesis and analysis.